as you see from your program, I'm due to give a talk on earthquake forecasting. Okay, so that is earthquake forecasting as distinct from earthquake prediction. Earthquake prediction, something you've seen on the telly, and is quite, I think, in the past, perhaps, has been regarded as the sort of holy grail of earthquake studies and efforts to reduce earthquake hazards. And probably maybe as long as something like 30 years ago, after the Haicheng earthquake in 1975, which was predicted, there was a lot of optimism about earthquake prediction. And you may have, I'm sure, well, I'm guessing you have seen things on the telly about earthquake prediction. But unfortunately, since Haicheng in 1975, despite various efforts, earthquake prediction has been elusive, to say the least. And basically, the community now has, I think for the time being, I think it's fair to say, more or less abandoned earthquake prediction and instead taken on the idea of earthquake forecasting. It's like weather forecasting, less precise than earthquake prediction. Earthquake prediction, if you think about it, needs to be precise within days, doesn't it? It needs to be on a human time scale as opposed to a geological time scale, which tends not to be so precise. And the location needs to be precise as well. Again, very difficult from a geological point of view. So earthquake forecasting is, for the time being anyway, has replaced earthquake prediction as a field of endeavor to reduce earthquake hazards. And there's a number of high-profile organizations that are involved in that. I mean, just to mention one, the USGS, United States Geological Survey Earthquake Hazards Program, previously called the Earthquake Hazard Reduction Program, but the same idea, to reduce the hazards associated with earthquakes. So what I want to do is just give you a little background to this, briefly, with some examples, including from the USGS, their efforts at earthquake forecasting, and then give a sort of a case study of some work in Central Asia, which is towards this endeavor, earthquake forecasting. Okay, so sorry about the macabre sort of image here, but I'm sure everybody in this room is of like mind that obviously what we're trying to do is to reduce, whatever we can do to reduce tragedies, earthquake tragedies. So earthquake prediction, I've already mentioned some of the stuff, but on initial look, if you remember of course, earthquake, the elastic rebound theory of earthquakes with accumulating elastic strain in the lithosphere, eventually overcoming resistant forces, rocks breaking or more likely pre-existing faults slipping to create the earthquake. And then that elastic strain continues to accumulate, and so there's a cycle called the earthquake cycle, in fact. But there are many variables in that. And in fact, G.K. Gilbert, a well-known American geologist, really expressed that perfectly over 100 years ago. And there's just too many variables, and as I say here, affecting the amount of strain that's been remaining in the lithosphere, the direction of stress, certain variables associated with stress, directed force, variables associated with frictional resistance to those rocks breaking, like fault strength, for example. And as I've already mentioned, earthquake prediction needs to be operating on a human timescale, which is inherently at odds with geological timescales. So, earthquake forecasting recognizes this, and but doesn't sort of throw in the towel, but seeks to make a contribution nevertheless. And it employs a range of approaches: instrumental, field geology, detailed field geology, remote sensing techniques, including drones, you'll be glad to know. And of course, many of the satellite-based platforms are useful in this, with the idea of being able to say something, particularly about big seismogenic faults. Obviously, well-known ones like the San Andreas fault, for example. Particularly things like long-term slip rates, which is, to some extent, I think I can say, has replaced, when I said earthquake prediction was the holy grail, the number one priority of earthquake forecasting studies is to determine slip rate, because that puts a number on the activity of a fault. So it quantifies and enables comparisons to be made between faults. Fault offset amount is all obviously the sort of thing you do with detailed field work. Recurrence intervals. There used to recurrence intervals. You note that I said recurrence intervals of characteristic earthquakes. Recurrence intervals used to be something that was, again, a sought-after goal in these earthquake hazards reduction studies. But of course, as typically is the case, the more data becomes available, the more one has to modify cherished models and in fact end up with, to a large extent, rejecting them. I might mention the recurrence interval. You say, okay, so the fault's slipping at this rate, and so that elastic strain accumulation is building up. So there should be an earthquake, big earthquake every couple of 300 years or something like that. But there's many examples of large earthquakes. The most probably immediately well-known example is the New Madrid. That's the correct American pronunciation, by the way. Madrid, not Madrid. But anyway, it's a place in central United States, Missouri or something like that. And they had 3 earthquakes there in 1812, over Christmas, 1812, 1813. 3 earthquakes of magnitude, approaching magnitude 8 earthquakes. Bang, 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 in about 2 months. So it throws into a cocked hat any idea of recurrence intervals. So recurrence intervals, so that's a problem perhaps. The type of fault slip, different styles of faulting, but overall we might say to establish patterns of tectonic strain release, which is what we're talking about. We're talking about accumulating tectonic elastic strain which builds up and then release as an earthquake. And of course, these patterns then, which can be recognized in the recent geological record, can be extrapolated into the future as the best index for the likely imminent behavior, the near future behavior of a fault. I might mention on this, of course, that seismometers, wonderful that they are, have only been around about 100 years, and therefore their record is too short to say very much about the long-term behavior of faults. And so the best information is obtained from the recent geological record, backed up where in some favoured places like the Mediterranean, we all know that's favoured, by archaeological data as well. Okay, a number of approaches, as I said, and I just, if you like, starting off with the sort of large scale, I imagine many of you might be familiar with this idea of the seismic gap theory. Okay, on the basis, one of the basic tenets of plate tectonics is that the plates are internally rigid and of very limited deformation. So the deformation takes place at the boundaries of these plates. We know that's not exactly true, but here's an example of the Pacific plate being subducted beneath the Kamchatka, Kuril, Japan arc here. And you can see there's a gap here. In other words, where parts of that subduction interface have not slipped. Okay, here and here, I've only got two hands, of course. Here and here, there's been slip, but in between, there's a gap where elastic strain energy is still stored and, in fact, increasing. And so, a gap like that is, on balance, likely to produce an earthquake before adjacent parts, simply because there's more elastic strain energy there. And, that needs to sort of, as it were, catch up. And in fact, this gap here was filled by the well-known Tohoku earthquake in 2000, the Fukushima power plant earthquake. Another earthquake forecasting approach that I might talk about a bit more next week, I guess, is stress transfer. So if we remember that the lithosphere, the upper part of the lithosphere, the seismogenic lithosphere, is storing elastic strain energy everywhere, including beneath our feet here, well, ground. Then if a fault moves within that strain energy field, that's going to disturb the field. It's going to change that field. That's the idea of stress transfer. And again, it's been on the telly with the North Anatolian Fault. Anybody come across the North Anatolian Fault on the telly with the westward stepping progression of earthquakes? It's okay to sort of own up about that. Nobody, you're kidding me.
I've come across the North Anatolian Fault, but not on telly.
Ah, it's shocking, isn't it? Okay, all right. Well, maybe we can put that glaring omission right later. Anyway, so basically, as long as you accept the idea that if a fault moves here, that's going to redistribute the strain energy, the elastic strain energy in the surroundings. And so here is the Tohoku earthquake, magnitude M sub W, moment magnitude 9, that took place on the 11th of March, all right? And that's the epicenter of that earthquake. What I want to show you here is this earthquake here, which took place on the 9th of March, 2 days before, which was a significant earthquake, magnitude 7.2. But of course, in the general background, it went unnoticed. Wasn't a particularly significant earthquake. But in terms of the stress redistribution, it loaded this earthquake here loaded this region which failed in the big earthquake 2 days later. So in hindsight, of course, which is a wonderful thing, in hindsight, it was recognized that that was in fact a foreshock of the big earthquake. Okay, one step further before I move on. Of course, the Tohoku earthquake itself, again, has redistributed the elastic strain energy surrounding it. And this is, this little image down here shows that. Here's the epicenter of that earthquake, excuse me. What time do I have to finish, Malcolm? Sorry.
Go after me, mate.
No, come on.
Somebody tell me. Bear with me a second.
Oh, God. Okay. All right. I didn't realise it was such a major.
12:45.
Okay. All right. Okay. Sorry. Reset. Carry on. So here is the epicenter of that, the Tohoku earthquake, magnitude 9 earthquake. And if you notice these warmer colours down here, this is an area of increased stress in terms of stress transfer. These are areas of reduced stress. Okay. And so, of course, and this is Tokyo, you won't be able to read that from where you're sitting, but so the Tohoku earthquake has loaded the segment of the subduction interface, which in fact last broke in 1923, the well-known Tokyo earthquake in 1923. And so this stress transfer, as it happens, that, if you like, straw didn't quite break the camel's back in this case, fortunately. But that approach, stress transfer, is another example of earthquake forecasting. Okay, so now I want to talk about the this case study. And you've all seen pictures like this. And this is a San Andreas in Carrizo Plain. And clearly, these two bits of crust, bits of upper seismogenic lithosphere have moved past each other. The question is, what is the rate of that movement? And I've already been through this. Maybe I didn't mention this, but I think it's pretty self-evident that a faster slipping fault is more hazardous. The strain energy is increasing more rapidly. I have this little analogy, of the clock spring analogy, I call it. If I can I indulge in that? Thanks. So if you think of clock springs, okay, winding a clock spring, so that is you imparting elastic strain energy into that spring. Okay. At plate boundaries, you have big faults and movement is concentrated. You have big springs being wound quickly, relatively quickly. So when that clock spring breaks, it produces a big earthquake. Whereas here, the smaller earthquakes we have here, you might think of that as a small clock spring being wound slowly. And so when that breaks, there's a smaller earthquake and they're less frequent. There's a relationship between fault length and earthquake magnitude. Okay, so I think that's dealt with all that jazz there. Before moving on, I just wanted to, talking about slip, just present this to you as a thought exercise. I know you're thinking all the time. But what's going on with a fault, say a big plate boundary fault like the San Andreas? There are a number of earthquakes, each represented by these shapes here. This is one example, this is another one, which contribute to moving that plate boundary. And in this case, so-called variable slip model, there are various earthquakes taking place with varying amounts of slip along the fault, so more slip here, less slip here, but overall you end up with a uniform slip along the fault. So that would tie in with the seismic gap idea I mentioned. Here's another model, another thought model, if you like, where again you have the net result of these earthquakes is that there's uniform slip along the fault. But in this case, there's big earthquakes take place repeatedly in one part of the fault to achieve that. And then finally, which, well, personally I'm more attracted to, is the so-called characteristic earthquake model, where different parts of the fault, different parts of this big plate boundary fault, are characterized by different characteristic earthquakes. The makeup of the plate boundary is such that those segments of the fault are characterized by, in this case, larger earthquakes. Okay, I think we can move on from that. And I just explain why I think that by this map of California. Okay, maybe we should start off over here, which shows that this is San Andreas Fault here. Okay, and of course in the textbooks the San Andreas is presented as a plate boundary fault, which it is, but in reality that plate boundary extends from the so-called California borderland offshore here all the way across into the basin and range. So there are many faults that are contributing to the slip between North America and the Pacific plates. Here, this is some historical earthquakes, in particular the 1857 event here, but this Owens Valley earthquake, 1906 San Francisco earthquake, and so smaller earthquakes down here. So there's if you look at this map and you look at this map and you think, well, the San Andreas isn't a nice simple linear fault. Actually, there's quite a conspicuous bend here, and in fact, this bend acts to restrain. In fact, called a restraining bend because, okay, here's the sense of movement, right lateral. If you have a bend in this sense, that's going to increase friction, isn't it? Frictional resistance at this. In fact, this is known as the Big Bend of the San Andreas Fault. So, in my way of thinking, it's quite likely that this segment of the fault is characterized by bigger earthquakes, like the 1857 earthquake, which was significantly larger than the 1906 earthquake. And so the characteristic earthquake model might be more applicable. Okay, I hope I've made that point. Are there any questions on any of that stuff? Well, I hope there's some questions at the end. In recognition of this variability in the plate boundary, the USGS, or actually USGS in collaboration with a number of academic institutions, comprising what's called the Working Group on California Earthquake Probabilities, which has been around actually for at least 20 years. This is their most recent forecast for California. And you can see the 1857 segment here, it highlighted in red, hasn't moved, so it's a seismic gap since 1857. Also highlighted in red is the southern San Andreas, which hasn't moved at all in historic times. And other faults which have moved in historic times, like the Landers earthquake, the Hector Mine earthquake, which have dissipated elastic strain energy and therefore have a lower probability of movement. You can see here, this is a forecast of magnitude 6.7 earthquakes or larger that over the next 30 years. And you can see here the 30-year, wait, maybe a bit small to see, likelihood in percentage. So these colours here are up between, this is a logarithmic scale, up towards 100% probability of an earthquake in that period of time. So this is an earthquake forecast. This is another style of earthquake forecasting. Here, the so-called fault readiness. How close is a fault to failure? You know, how near is the elastic strain energy accumulation to the point where it's overcoming or about to overcome frictional resistance. And again, here, the southern San Andreas and the Big Bend of the San Andreas are regarded as ready. So they are ready to produce big earthquakes. Here, the Landers fault earthquake and the Hector-Mine earthquake show that, you know, very low readiness simply because they've produced recent earthquakes. Note that the San Andreas that broke in 1906, low readiness, but other faults in the Eastern Bay Area, like the Hayward and Calaveras faults, which were very active before 1906, in fact. We can talk about that more, are identified as now of high readiness. So it's another example of earthquake forecasting, based primarily on slip rates. We're putting a number on the rate of movement. Excuse me. So here you can see these, without going into detail, I think you get the picture. This is for the Bay Area, obviously an important area of earthquake hazards concern. This is for the Los Angeles area. Okay, so now I'd like to spend, 15 minutes. I hope there'll be some questions at the end, but have lunch, on this case study of an area in the Tian Shan Mountains, okay, in Central Asia, which is an area of active compression associated with the northward movement of India as an indentor, India moving northwards, dragged by subduction at a rate of something like 50 millimeters a year, ploughing into the southern margin of Asia. Ploughing in, it has been ploughing in for something like 45 million years, and in that time has, in a snow plough fashion, ploughed in something like 2,500 kilometers. I expected to hear gasps of disbelief from that. Maybe I didn't get that across. So India, as a subcontinent, has ploughed into Asia to the extent of 2,500 kilometers in the last 45 million years. Thank you. Thank you. More like it. I know, it's so difficult in Asia, I suppose, in the YouTube generation. It's very difficult because always there's something more impressive on YouTube. No matter what, there's something more. So it's difficult. I mean, to me, this is amazing, but you know, check on YouTube and something even more amazing. So, and this is from the World Seismic Hazard Map, and it shows this area in the highest hazard level. So this is an area of extreme earthquake hazard, okay? And you can see generally the Alpine Himalayan belt is identified through here. PGA, by the way, I'm not sure you've come across that, peak ground acceleration, a measure of how, what percentage of G or even exceeding G, the acceleration due to gravity, an earthquake produces. It's a parameter that's used particularly by engineers in designing things. Okay, so this case study will focus on this fault here, the Talus Vagana fault, which, as you see, bisects the Tian Shan mountain belt. Okay, and it's just ahead of the Pamir indentor. Okay, which is, if you like, the northwestern corner of the Indian subcontinent, moving into Asia, as I say. This is very old work by Molnar and Taponnier, well known, that associates this indentation idea using a plasticine model. We can certainly discuss this in a critical way with other models like the viscous sheet model, but for the time being, I think this is pretty self-evident. We've got India moving here. This is the Talus Vagana fault we're concentrating on. This is the Pamir indentor. Okay, and various other faults, well-known faults like Altin Tile fault. And here are these faults. And the idea is that these terrains really are moving aside on these big strike slip faults in response to the northward movement of India. So we're, as I say, we're going to be looking at this fault. This is a map of the Tian Shan with the Talus Vagana fault, and these arrows are GPS vectors. Okay, so satellite measurements that document the amount of movement in real time. And so what this is showing, each of these vectors, there's a scale. Here we go. Here's a scale here. Okay, these vectors show something like 20 millimeters a year contraction rates across the Tian Shan. Again, I thought at least a couple of sharp intakes of breath, but no. Okay, all right. But that's amazing, isn't it? 20 millimeters a year of a mountain belt being squeezed in real time as we speak.
How much volume is it?
How much volume?
Yeah.
What's the scale? Oh, we've got the scale. Well, we've got. Yeah, it's a big area, certainly, and presumably this contraction is, well, yeah, not presumably. Clearly, this contraction is being accommodated by elastically. It's like, is there a ruler or something? Like this, if I may. So here, look, this is this cup, right? If I deform that, imagine that's the Tian Shan. It's being squashed like this, isn't it? That's being measured. And what I'm doing, if you care to do this yourself, you can feel there's some spring in that. That's the elasticity I'm talking about. If I were to take away that, it would recover. So that's the definition of elastic strain. So that elastic strain is accumulating, as I said, as we speak, across the Tian Shan. Well, from the point of view of slip rate studies, this case study I want to finish with here, most significantly, and to me, you know, it's one of those things that demands more explanation. What's unsatisfactory to me is that here you have this major fault, which is a significant feature, as you'll see in a moment. But on the GPS data, as I think you can probably appreciate from this, the fault is essentially invisible. So even though this is contracting at 20 millimeters a year, the Talus Vagana fault is, well, in the relevant paper, the estimate is, this is where the Talus Vagana fault is here. The estimate is, they based on these GPS readings, that the slip on the Talus Vegana is less than 2 millimeters a year, which doesn't make sense geologically. It does make sense if you're just considering elastic strain. But of course, what's a fault? A fault is permanent strain, isn't it? A fault, by definition, is where there's been movement, and therefore that's a permanent strain, not recoverable. But of course, the GPS is only, in this case, I think something like 27 years worth of data. This is a very good GPS network, by the way. But inherently, GPS satellite data is only a short snapshot of time, and in fact only only likely to be recording elastic strain energy, so not including what we're concerned about, fault displaced with big earthquakes that produce permanent strain. So that's the point I'm making here. Obviously, the earthquake cycle, the accumulation of elastic strain energy to breaking point, could be measured in potentially thousands of years, certainly hundreds and thousands of years. And so how representative is a geodetic record of a couple of 3 decades? Also, in terms of earthquake hazards, you're just measuring elastic strain energy, aren't you? Interseismic elastic strain energy with GPS. How valuable, how representative of that is that of the behavior of that fault? If you're not even capturing one event on that fault, are you? All you're capturing the elastic strain accumulation while that fault is locked in its interseismic mode, if you like. Okay. So, here's the Talus Vegana. This, you can see this east-west structural grain here, I hope, of the Tian Shan and the Talus Vegana fault. So right away you think that doesn't look like a fault that's moving. Subjectively you just think, well, that doesn't look like a fault that's moving at less than 2 millimeters a year. To me, anyway. Also, on this little inset map, I might come back to this, you can see that these other faults that I showed you on that earlier slide, like the El Tintag fault, the Karakoram fault here, are moving at rates that, around about sort of 10 to 15 millimeters a year. So on that view, a Talus Vegana fault slip rate of less than 2 millimeters a year is anomalous to me. Certainly unexpected. So here's an approach to this. Okay, so we've got a map here, all right, that shows who's heard on the telly again, perhaps. Who's heard of Wallace Creek on the San Andreas Fault? You are kidding me. Are you? Yeah.
Sorry, we just don't watch TV.
Yeah, you're pulling my leg again. Nobody's heard of Wallace Creek on the Carrizo Plain on the San Andreas Fault. Okay, so right, reset. Necessary background information. Okay, all right. Well, this is the same kind of approach as Wallace Creek. I invite you at some stage. Basically, what we have is a stream. The interaction between the fault. Okay, here's the fault, which is a right lateral fault. The interaction between that fault and this stream. Okay, together with some C14 dates. Here is the picture, the overview, and here's the map. I hope you can sort of flip between the two. Here's the fault, right, sort of rippling across the countryside here. And here you see a former position of this drainage. Okay, drainage used to flow along here and flow down. I hope you can see, flow down like that. Okay, so this is that paleo drainage, the blue dashed line. See, like this flood now abandoned. The reason it's abandoned is because with successive faulting events, one of those faulting events, probably this, one of those faulting events was just a step too far, and the stream couldn't reconnect with its downstream continuation. And consequently, it cut a new course straight across the fault. Okay, so it couldn't maintain this long deflected, of course, this long bent course, and instead jumped across the, straight across the fault, down slope. And in doing so, of course, because the gradient was much reduced then, it down cut, and that's caused this conspicuous down cutting, entrenchment, and you can see that up here. See the down cutting, and so consequently the gravels, these stream gravels, when the river stream, intermittent stream flowed here, were abandoned here on this little bench here. So, and it's those the timing of that abandonment that you want to get, because if you combine that date of the abandonment with the amount of post-abandonment movement on the fault, okay, which as you can see has begun to deflect the entrenched stream in turn, you have a slip rate. You have a distance and you have an age. And so this becomes then an opportunity, a place where there's an opportunity to get a slip rate. And so trenching studies to expose those gravels, those paleo gravels, from this now perched and abandoned channel, and measuring the distance. Basically, there's a number of piercing lines here, and the best estimate for the amount of post-entrenchment displacement is about 70 to 75 meters, okay? So then the question is, well, what's the age of those gravels? Yeah, this just shows some of this displacement. I don't think we could need to dwell on that. I hope you. This is an exposure. This is the trench. It shows the Talus Vagana fault here with some little local compressional component, quite common, of the overthrusts, these distinctive white marble-rich gravels across this. These gravels derive from the other side of the fault. There's colluvium, and here at the bottom, that colluvium is overlying the paleo-channel gravels that I've been talking about, that were abandoned when that entrenchment took place. And so basically getting dates and calibrating and various other things, you end up with a slip rate of, something like 14 to 15 millimeters a year. In other words, a bit more in keeping with what you might expect. Okay, if I quickly give you one other example of, this is about 10 kilometers away, a place called Sari Bulak. Have I got that? Sorry, no, us to say the previous place was Sari Bulak. Here again, we've got the same situation with a former course of this drainage being deflected in a long, awkward bend along the talus Fagana fault. Okay, and again, that situation is not sustainable long term, and so at some stage, probably associated with a faulting event, the drainage cuts a direct course across here, and in doing so, cuts down because of the shorter distance, steeper gradient, down cuts, and produces a new entrenched channel, incised channel, leaving this abandoned, and again some perched gravels that, with a bit of effort, one might expose in a trench. Since then, since that event took place, this entrenchment event, there's been something like 55 to 60 meters of offset. Okay, here is, I think I may have indulged in a bit of yes, okay, bit of animation. It's important that you believe me on this paleo channel position here, and there is plenty of evidence for that in the field. All right, sorry, subject you to that again, but get the idea, I hope. Okay, this is the trench exposure in the perch gravels from that paleo channel. These are the gravels here, in that paleo channel gravel, and again overlain by colluvial units derived from upslope. Okay, and again, of course, C14 dates, and again, you end up with this slip rate. Sorry, this is a PDF version, not so good, but I just wanted to. So the end result of this effort is to revise the talus Fagana slip rate from less than 2 millimeters a year up to between 11 and 16 millimeters a year. In other words, something that's quite in keeping with other faults associated with this indentor, and in keeping with the topographic expression of this fault. So, it summarizes basically what I think. Yeah, although these, you may think, 11 to 16 millimeters, that's not very precise, but certainly, and you might say, okay, so you're very sure about that or something. Well, without going into a lot of detail, yes, I am sure about that. But if you want to argue that in fact the slip rate's less than 2 millimeters a year, then the field data has to be out by something like an order of magnitude. And even somebody of such modest field abilities as myself is not going to make an error of order of magnitude. So that 75 meters I showed you, that would have in fact been 7.5 meters, and that just doesn't wash. Really. Okay. Any questions? Or who would like to ask the first question? Yes, good.
Are any of these methods currently used by governments?
Oh yeah. Like I said, USGS earthquake. Yeah, well, absolutely. It's all standard. The trick is finding the field localities to do these things. And there's a number. The dating is very important. I can show you some other stuff elsewhere on San Andreas, for example, where I'm trying to use OSL dating, optically simulated luminescence dating, because there's not material for carbon-14. Some other studies have used, for example, dendrochronological dating, particularly on the Cascadia subduction zone So these are, the trick is identifying the favourable field locality. Yes, good. Thank you. Questions. That gives me, I think that, oh, somebody was listening.
I think it's just for curiosity. When you have like multiple faults in an area,
Yes.
when you report peak ground acceleration, do you measure it from just one fault, or do you combine data from many?
Well, you touched on a couple. The peak ground acceleration is an instrumental, use a strong motion seismometer, and so it's a measurement derived from an earthquake. Okay. The other thing I thought you might have mentioned was the fact that I think this has been mentioned already. When you look on a map, you see the fault as one line, but in reality, you're dealing with a fault zone. And so slip rate studies like this, and I can show you maybe on whenever it is next week. There are a number of faults involved, involved in the movement on that fault zone. And so if you only study one of those faults, the most prominent one, perhaps, you're not getting the full picture. Other questions? Yes, good.
Maybe I didn't understand.
Oh. Maybe I didn't explain properly.
You talked about the readiness. That
Yes.
it's possible to evaluate the readiness, but how? I mean, how can you evaluate how much?
Well, okay,
is
yes.
accumulated?
Based on slip rates determined by methods like this that I've just explained. So faster slipping faults, all other things being equal, are going to be more hazardous, and particularly based on the faulting history of that fault. If you remember the image, it showed like the Landers, the fault that broke in the Landers earthquake and the Hector Mine earthquake in the 90s as low readiness, because the idea is the faulting event dissipates the elastic strain energy, so that's low readiness. Whereas other places like the southern San Andreas, not broken in historical times. I mean, historical times aren't very long in California, but not broken in historic. That means the elastic strain energy has had longer to accumulate, and therefore the fault is more ready, because what we're talking about is how close to the frictional resistance of the fault being overcome by the elastic strain energy. How close we are, that's what readiness is, if you see what I mean. So does that better explain things?
Yeah.
Slightly. Okay,
I
well.
thought there was like some.
No. I mean, it's all earthquake forecasting. It's like weather forecasting. I think I mentioned. It's not going to be precise, but it's a whole lot better than nothing at all. And as more data becomes available, more different, improved methodology, improved technology, then there's every reason to think that earthquake forecasting will be more and more useful. And ultimately, maybe, I don't know, whenever, earthquake prediction, which must be an instrumental effort, will resurface. I don't know. To me, the animal behavior, there are many reports of anomalous animal behavior prior to earthquakes. And so that's a fact. There's innumerable descriptions of that, but that's not being studied, or hardly being studied, because it's not viewed as very scientific. But to my way of thinking, that's an omission. It should be more systematic studies of animal behaviour. And there's a couple of researchers, I think, in Japan there's somebody who has a load of snakes, as I remember, and in China, I think, somebody with goldfish, studying the behaviour of goldfish prior to earthquakes.
Can I have one?
Yeah, by all means. I mean, am I about to be dragged off?
Okay, if you get this slip rate,
Sorry,
if you have slip rates,
slip
for
rates, yes.
example, you have an area with multiple faults, and you know the slip rate for each one.
Yes,
you
that would
come
be
up
an...
with like a map that shows possible.
Yeah, absolutely. There are, like California is going to be the best example of this, simply because of the effort put into the work there.
But can we predict a magnitude for future earthquakes for a certain fault?
You remember one of the parameters I had up was the amount of slip.
Yeah.
So, for example, in the Carrizo Plain, which I hope you've seen with those stream offsets, it's possible to show the amount of slip in one event based on stream offsets. Have people seen those? Come on, please.
Yeah.
Joking. Very interesting. If I may leave you with this final, Malcolm, 30 seconds. Yeah. Okay. Very, very, very interestingly, in the can I think everybody's roughly idea? It's in all the textbooks. The Carrizo Plain that I showed you there with all the stream offsets. Thank you.
Yeah.
Very interestingly, those stream offsets showed that in 1857, the 1857 earthquake I mentioned on the Big Bend, the offsets in the Carrizo Plain were something like 11 meters. 11 meters of co-seismic offset. And then that stopped rather abruptly. So you have a profile of a high slip rate, a high offset in that event, and then that sort of dropping off, which was always a bit sort of a bit unsatisfactory, a bit puzzling. And more recent work has shown that in fact that offset amount measured on those streams of 11 meters actually recorded two events, the 1857 and the previous event. In other words, the rate at which in the Carrizo Plain the streams are being cut and refreshed is less than the rate of or the frequency of earthquakes. That's amazing. That, by the way, just to mention, that's amazing. So in other words, and so that's cleared up that problem, because suddenly the Carrizo Plain slip rates in 1857 go down from 11 meters to something like 5.5 meters, much more reasonable. But anyway, I thought that's the 30-second party shot. Very, very. Isn't that interesting that the renewal rate of those stream channels is less than the frequency of big earthquakes? So it's a dry place with not much rainfall. Yeah. Okay. Any questions? You know where I am.